Thank you very much. So a unit distance graph is a graph whose vertex set is a subset of RD, and where we can put an edge between two vertices if their distance is 1. But in our case, we don't have to. So there may be 2 points that are a distance 1 from each other, but there is no edge between them. And if a graph is isomorphic to a unit distance graph in RD, then we say this graph is embeddable in RD or has a unit distance embedding in RD. Also, if we restrict the set of points on the sphere, on some sphere of radius 1 over square root 2, then instead of distance 1, we can think of orthogonality. So then 2 points are distance 1 apart from each other, if and only if the corresponding vectors are orthogonal. And we want to know for certain graphs which is the lowest dimension in which we can embed it as a unit distance graph. And this is the Euclidean dimension of G. Also, if we can do it on the sphere, then in RD, then G has spherical dimension D. Here are some examples. The first two are obvious. These are just simplices. The third one is K33, which is not embeddable in the free space, but we can embed it in R4. We can also do it in R4 on the sphere. We just take two orthogonal planes, and in both of them we take circles centered at the origin of radius 1 over square root 2. And we put the first class on the first circle, the second on the second. And we can do the same. We can say something similar regarding the chromatic number. So if the chromatic number is k, then we can embed the graph on the sphere of radius 1 over square root 2 in R2k. We just take k pairwise orthogonal planes, and in each of them we take a circle of radius 1 over square root 2, and to each class we assign one of the circles and embed the vertices from this class in that circle. So Erdos and Simonovich asked if it is true that if the number of edges of a graph is less than d plus 2 choose 2, then it can be embedded in RD. And this is exactly the number of edges of a d plus 1 dimensional simplex. And of course, this is not true for in the free space because of case 3. And there were some results for smaller dimensions. So it was proved for dimension 3. No. Okay, I think I misspelled it, but I mean, for dimension 3, it was proved for 1 less. So if we has okay, so it is true for 3 and for 4. And also for dimension 4, there are only 2 graphs with 15 vertices that cannot be embedded in R4. And it is also true in general for larger values. And moreover, if the number of edges is less than, if there are no subgraphs that are isomorphic to kd plus 1 and kd plus 2 minus a triangle, then we can also embed it on the sphere. And I would like to tell a few words about the proof. So in that paper, they proved that if the maximum degree of a graph is at most d minus 2, then the graph can be embedded on a sphere of radius 1 over square root 2 in RD. And the proof of it is easy. We just add the points to the embedding one by one. So say we have been embedded some of the points so far, then we take the next. Then it has at most d minus 2 neighbors. So those neighbors of it that are already on the sphere span some subspace of dimension at most d minus 2. So their orthogonal complement has dimension at least 2, which intersects the sphere in at least a circle, and we can choose a position from the next point from that circle. And we can generalize this lemma, so we don't need that strong thing. It is also enough if the graph is d minus 2 degenerate, which means there is an ordering of the vertices such that each vertex has at most d minus 2 neighbors of smaller index. And then we can do the same. Then we take such an ordering, which proves the d minus 2 degeneracy, and then we add the points to the embedding on the sphere one by one according to this ordering. So if the graph is d minus 2 degenerate, then we are already done. Otherwise, there must be a subgraph of minimum degree at least d minus 1. And this subgraph cannot have too many vertices because of this condition on the number of edges. And also it cannot have too few vertices because of this condition on the minimum degree. And we first deal with this subgraph of minimum degree d minus 1, and then we add back. We add to the embedding the other vertices. And so I don't want to tell more about this, but I would like to talk strengthening of this result. So we can say something one stronger. If the maximum degree is at most d minus 1, then we can embed the graph on a sphere in RD. And if the maximum degree is d, then maybe we cannot embed it on the sphere in RD, but still we can embed it in the space, except for this, for case 3. And these are best possible because we cannot embed the simplex on d plus 1 vertices on the sphere, and we cannot embed the simplex on the d plus 2 vertices in the space. Yes, so first I'm going to sketch the proof of the first one. To do this, we need this combinatorial lemma. It says we can partition the vertex set of any graph into two parts such that in both parts, the maximum degree of the graph induced by those parts is at most half of the maximum degree of the original graph. And when d is even, we can say something a bit stronger. So we can still have that in the first part, the maximum degree is at most half of the original maximum degree. And in the second part, it can be one less. And using this lemma, we can prove the first part by induction. So for small values, it's easy. For example, for 3, we have that the maximum degree is at most 2. So the components are paths and cycles. So we just have to embed paths and cycles on the sphere in the 3 space, which is easy. And for larger values, we do induction. First, we take a partition like this lemma, and we choose d half, a subspace of dimension d half for this first part. We take a spare in it, centered at the origin, and we embed the graph induced by the first part on this sphere. And then we take the orthogonal complement of this subspace and And by the induction, we can embed the second part on the sphere of radius 1 over square root 2 in this second, so in the orthogonal component. And then we are done because the distances between any 2 points from the 2 spheres we used is 1. Okay. And from this second part, I'm only going to talk about the even case, because for the odd, it is a bit more complicated. First, we need strengthening of the combinatorial lemma. So if D is even and the maximum degree of a graph is at most D, then there is a partition into D half parts, such that in the first D half minus 1 parts, the maximum degrees induced by these parts are at most 1. This is the first condition. So there are independent edges and maybe some single vertices. In the last part, inside the maximum degree is at most 2, so there are cycles and paths. And the third condition says if there is a vertex of maximum degree 2 here in this last part, then this vertex has exactly 2 neighbors in all the other parts. And so this is the second part of the theorem we want to prove. So again, we have that D is even now, and the maximum degree is D. Then we can embed our graph in RD. We start with a partition given by the previous lemma. And first, we remove the degree 2 vertices from here until we get something here of maximum degree at most 1. So we remove an independent subset of vertices. Oh, two edges are missing here. Just 2 more. So we remove a maximal independent subset of degree 2 vertices from here. Then no edges here. And what is left here? So now here we also have max degree at most 1. And we first embed this part on a sphere, and then we will add back these removed vertices. First, we look at the first part, say, and we choose a plane, and embed this first part in this plane on a circle of radius 1 over square root 2 centered at the origin. But we do that such that there are no points in opposite position. And then we take a plane orthogonal to this first plane, and we embed the second part in the second plane in a similar way. And we do this with the other parts as well. So these circles are in pairwise orthogonal planes, and in none of them, so there are no points in opposite positions in none of them. And now we would like to add back these removed vertices. So to do this, we have to see where are the neighbors of one of them. So we pick one of them. It has exactly 2 neighbors in all of the parts because of the structure that we get from the lemma. So we need to see what is the subspace that these neighbors span. And this will be an affine subspace of dimension d minus 1. And because we embedded the points on the circle such that there were no points in opposite positions, this subplane doesn't contain the origin. So there will be exactly 2 points. Yes, and this subplane cuts the sphere in some subsphere, and there are exactly 2 points, this and this, that are at distance 1 from all of the points of this subsphere. And because this affine subplane doesn't contain the origin, these 2 points are not on the sphere. So now I go back to this picture, and now we can add back the removed vertices. We can do it one by one, because there were no edges between them. So we only have to care about their neighbors in this part. And from that thing, we know for each of them we can choose from 2 points. But there could be problems, say for 2 of them. No, there could be problems if there were 3 points in this last part, such that they have the same set of neighbors, because then we should choose the position for 3 points, but we have only 2 points where we can put them. But this cannot happen, because any point from this last part were originally from this part. So if there were 3 with the same set of neighbors, then they also have the same set of neighbors here, but here inside the maximum degree was at most 2. And another problem could be if 2 different set of neighbors. So the set of neighbors of 2 different points from this last part would span the same affine subspace. But this also cannot happen, because if the set of neighbors are different, then they are indifferent in at least one of these parts, say in this. So then they intersect this plane in different points. And then the corresponding 2 points are also different. So this finishes the proof. And so thank you very much for your attention.